Hello and welcome to a video series on improper integrals. In this first part of the series, we shall explore the type 1 improper integral. The second part will include the type 2 improper integral, and the last part will demonstrate how to use these with examples. So our objectives for the whole series are as follows. We're going to determine the type of improper integral presented. We're going to determine how to define a convergent or divergent improper integral. We're going to determine how to perform the integration when the interval is infinite. We will also determine how to perform the integration when a singularity occurs at an endpoint. And finally, we will determine how to perform the integration when a singularity occurs in the interior of an interval. So materials for review include the domains of functions, limit evaluations as input approaches an infinity, and, of course, definite integration. So just as a quick review, the extreme value theorem states that if f is a continuous function on a closed interval, ab, then f attains an absolute maximum value, some f of c value, and an absolute minimum value, some f of d value, at some numbers c and d in the closed interval a to b. Now, the important thing to notice here is that infinity is not considered a number, so it is never part of a closed interval for our class, which means that the interval AB is a finite interval. Here is the definition of a definite integral. If f is a function defined for x between a and b, including a and b, we divide the interval, the closed interval, a to b, into n subintervals of equal width, delta x, where delta x is computed as b minus a divided by n. We let x sub 0, which happens to be a, the left endpoint of the interval, x sub 1, x sub 2, all the way up to x sub n, where x sub n is defined as b, the right endpoint of the interval. So we're going to let all these x's be the endpoints of these subintervals, and we let x1 star, x2 star, all the way up to xn star be any sample points in these subintervals. So x sub I star lies in the ith subinterval, x sub I minus 1 to x sub I inside the closed subinterval. Then the definite integral of f from a to b is given as the limit as n approaches infinity of the summation from I equal 1 to n of f of xi star times delta x, provided that this limit exists and gives the same value for all possible choices of the sample points. If it does exist, we say that f is integrable on the closed interval ab. Now, with this definition, although it's pretty long and wordy, essentially what it is saying is that if we were to take a closed interval ab, which again, a and b are finite numbers, and we divide up the interval into subintervals, select points inside each of those subintervals, we should be able to approximate the integral by using a finite sum. It's taking the limit as n approaches infinity, essentially the number of these sample points extends to infinity, that we get this integral. Now, for type 1 improper integrals, these are where we consider infinite intervals. So, if the integral from a to infinity of f of x dx exists for every number t that's greater than or equal to a, then we may also conclude that the improper integral from a to infinity of f of x dx is equal to the limit as t approaches infinity from a to t of f of x dx, provided the limit exists as a finite number. Now, comparing this to the definite integral definition allows us to use all of our knowledge and understanding of the definite integral. So essentially what this is asking us to do is that it's asking us to back off the infinity, have a finite interval that happens to be closed, This way I can apply the definition of definite integral. And we know from the fundamental theorem of calculus that the evaluation of a definite integral results in the difference of antiderivative values from the endpoints. So we are going to use that fundamental theorem of calculus to evaluate the antiderivative at the endpoints of the definite integral. And then we will use that t value as a parameter in the antiderivative and evaluate the limit as t approaches infinity. A similar definition for when we have negative infinity as our lower endpoint on our definite integral. So if the definite or the improper integral from negative infinity to b of f of x dx exists for every number t that happens to be less than or equal to b, then the improper integral from negative infinity to b of f of x dx happens to be equal to the limit as t approaches negative infinity from t to b of f of x dx, again, provided the limit exists as a finite number. So this is, again, the same idea, is that we are taking these infinite intervals, backing off the infinity, so that I can have a finite interval. I can then apply the definition of the definite integral and evaluate this using the fundamental theorem of calculus. I get the antiderivative at the endpoints. I take the difference in the antiderivatives, and then I evaluate the limit of this parameter t as it approaches negative infinity. The improper integrals from a to infinity of f of x dx and from negative infinity to b of f of x dx are called convergent if the corresponding limits exist. These improper integrals are called divergent if the limit does not exist. If these improper integrals are convergent, then we may say that the improper integral from negative infinity to infinity of f of x dx may be written as a sum of improper integrals from negative infinity to a of f of x dx plus the improper integral from a to infinity of f of x dx, where any real number a may be used. So if we know that our improper integrals from a to infinity and from negative infinity to a, if we know that those exist, then we do have this additivity property with improper integrals as well. Remember, one of the properties of definite integrals is that I can pick a point somewhere inside the interval a to b where I can sum up the individual pieces of the integrals. We can do the same thing with improper integrals, provided that we know that we are able to split them up into convergent pieces. If either one of these integrals is divergent, then we cannot evaluate the improper integral from negative infinity to infinity. That will also be divergent. So let's look at an example on how to evaluate a type 1 improper integral. Determine whether the integral from 1 to infinity of dx over x is convergent or divergent. So we're going to proceed as follows. We're going to take our definition of improper integral. So if the improper integral from 1 to infinity of dx over x will be equal to the limit as t approaches infinity from 1 to t of 1 over x dx. Now we know that the integral of 1 over x dx happens to be the natural log of the absolute value of x. So we're going to evaluate that definite integral, and we have the limit as t approaches infinity, natural log of t minus natural log of 1. The natural log of 1 is 0, and when we take the limit as t approaches infinity of the natural log of t, because of the continuity of natural log, we can conclude that this is also infinity. Since the limit is not a finite number, this integral happens to be divergent. In our second example, we're going to consider the integral from negative infinity to 0 of x e to the x dx, and we're going to see if this is convergent or divergent. We do the same process. We take that improper integral from negative infinity to 0 of x e to the x dx. We're going to back off that negative infinities to get our definite integral. So this is going to be equal to the limit as t approaches negative infinity from t to 0 of x e to the x dx. Using integration by parts, we can evaluate that integral, and we get the limit as t approaches negative infinity of x e to the x from t to 0 minus the definite integral from t to 0 of e to the x dx. When we evaluate these integrals, we have the limit as t approaches negative infinity of negative t e to the t minus 1 plus e to the t. Now, in order to evaluate this limit, we're going to need L'Hopital's rule. So the part in red, if you happen to observe this, the negative t e to the t, that part is in red because that's the part we need L'Hopital's rule with. So when we use L'Hopital's rule to evaluate that first part, we end up with negative 0, if you will, negative 0 minus 1 plus 0, and that's going to be equal to negative 1. The limit exists as a finite number, so therefore this integral is convergent. So the integral from negative infinity to 0 of x e to the x dx happens to be equal to negative 1. In our third example, we're going to determine whether the integral from negative infinity to positive infinity of 1 divided by the quantity 1 plus x squared dx is convergent or divergent. In this case, we're going to choose an interim value of a equal to 0, and this is a convenient value due to the symmetry of the graph of 1 over 1 plus x squared. So we're going to split up this integral from negative infinity to infinity of 1 over 1 plus x squared dx. We're going to split that at 0. Now remember, this integration should work for any value that we choose to split it at. So we choose 0 because it's nice and convenient. So we have the integral from negative infinity to 0 of 1 over 1 plus x squared dx, plus the integral from 0 to infinity of 1 over 1 plus x squared dx. We're going to evaluate the integral from negative infinity to 0 of 1 over 1 plus x squared dx first. Following our same steps that we did, we have the limit as t approaches negative infinity of the definite integral from t to 0 of 1 over 1 plus x squared dx. We know that this integral happens to be the inverse tangent or the arctangent. So we have the limit as t approaches negative infinity of the inverse tangent of x evaluated from t to 0. We go ahead and substitute those values in. The inverse tangent of 0 is 0. And when I take the limit as t approaches negative infinity of the inverse tangent of t, we get pi over 2. Now we go ahead and evaluate the other integral, the integral from 0 to infinity of 1 over 1 plus x squared dx. Again, the same process. We have the limit as t approaches infinity from 0 to t of 1 divided by 1 plus x squared dx. Again, the inverse tangent results, and we have the limit as t approaches infinity of the inverse tangent of x from 0 to t. This again becomes the limit as t approaches infinity of the inverse tangent of t minus the inverse tangent of 0. We know from our previous calculations that the limit as t approaches infinity of the inverse tangent of t happens to be pi over 2. Since both of these integrals are convergent, we may conclude that the integral from negative infinity to infinity of 1 divided by 1 plus x squared dx is equal to the sum of the integrals from negative infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. We've calculated both of those to be pi over 2, and pi over 2 plus pi over 2 is pi. Therefore, this integral happens to be convergent. In our next video in this series, we will consider type 2 improper integrals, which is where we have a singularity at the end point of the interval. So thank you for your time and attention.